All right, so we are now going to look at the player of motion and rotational kinematics of how fast. So, how fast, we know from our discussions of translational motion that it's the amount of distance covered or of displacement covered per time. And so if we look at that in terms of rotational kinematics, it's the same thing, and we can think about it, and again, two different ways. We can think about it in how much distance the object has covered per time as it goes through this rotation, and we can think about how much angle the object has covered per time as we go through this rotation. So let's first start about the angular piece. So what we refer to as the angular velocity. Now, for angular velocity, we use the Greek lowercase letter omega. And just like our ideas of translational motion, angular motion is how much angle we cover per time. So our change in angle, our angular displacement per time. And again, we're always going to be working in radians, just as a reminder. All right, well, what about the translational velocity of this object? How fast it's moving if I imagined it as moving linearly? And we're talking about a very specific velocity. We're talking about a velocity at this point that the object is rotating. And this is the tangential velocity of the object. So the object's tangential velocity, how fast is it going if it were going in a straight line at that point in the rotation? And since we're going to look at that tangential velocity, let's look at what, again, that means. Now remember, we know that the distance that it's going to travel, we're going to talk about this as a tangential velocity, so velocity tangential, is going to be equal to the arc length per time. Okay, so equal to the arc length per time. So imagine this is going at a constant velocity for the sake of our introduction. Well, we know that the arc length per time is going to be the arc length, which is theta times the radius per time. And if I organize these, I end up with theta per time times the radius. And I see that my theta per time can be written as omega times the radius. So this gives rise to the velocity, the tangential velocity of an object as it's rotating about a circle. It's going at a certain angular speed at that point in time, and that angular speed gives rise to that tangential velocity by the angular speed times the radius. So again, and I'll just make these easier to read on the board, we have both a relationship for an angular description and a tangential or more linear description and the relationship between the two. All right, good job.